All right. So far what we talked about, we're in probability. We talked about probability. We talked about the basic rules of probability. We talked about conditional probability. Now that we're past conditional probability, we went into what we call our fundamental counting principle, and we talked about permutations and combinations. And there's a reason that we did that, all right? The reason that we did that is because, y'all are asking me, come on, answering everybody. I don't know. Okay. Yeah, the test, somebody asked for the test. The test is 2 weeks from now. It's not this week, it's the fall. It opens up at the end, it opens up on this Sunday though, the 28th. And it closes next Sunday, which is Easter. Yeah, got that? People are asking questions. All right. Anyway, like I was saying, so what we're doing now is we've talked about permutations and combinations. And the reason that we did that is because this next part of what we're talking about, we call it random variables. And in our random variables, what ends up happening is there's these different combinations that we can make. All right, there's different combinations that'll give us the exact same probabilities. And we'll talk about that in a few. But we're gonna start off with what's called a random variable. And a random variable itself, right, is some kind of numerical variable. It is numerical. Remember we gave numerical variables a name. Does anybody remember what we call a numerical variable? If a variable is a number, a number. Does anybody remember what we call that kind of variable? No, you know.
No, I don't remember.
It starts with a Q. It starts with a Q. Two types of variables. They're either categorical or
quantitative.
they are quantitative. Good job. So these numerical variables are quantitative variables. Every random variable is a quantitative variable. They're all quantitative. And remember that these variables, when we have quantities our quantitative variables do one of two things. Numbers can do one of two things for me. What do they do? Does anybody remember what they do?
Count,
those variables
measure.
do one.
Count.
Good, they countermeasure. Good job. They countermeasure. If they count, we say that the variable is, because somebody remind me what we call a countable variable. What do we call a countable variable? Anybody? None of y'all? What about a measurable variable? Do you remember what we call that?
Continuous or this?
Good. Measurable is continuous. The other one is called what? You were saying it, I'm sorry.
Discrete.
Discrete. And a discrete variable, if it's countable, it's a discrete. Discrete means that it has to be a whole number. It has to be a whole number. Continuous variables can be fractions or parts. That's what I want to make sure we understand that. That is the basis of what we're doing right now, right? So in these particular variables, we have a numeric quantity. So some kind of number outcome. The outcomes are going to be numeric. But what happens is we can assign a probability to each outcome. And that probability itself is left up to random chance, left up to chance, all right? That's why it's called a random. The word random means you're leaving it up to chance. The outcomes are unknown because you haven't did the actual experiment yet. But each probability for the outcomes that are possible are known. And what do I mean by that? So here's a random experiment we could do. Let's take a die and roll it. Let's take one die and roll it, right? What are the possible outcomes? Can anybody tell what the possible outcomes are?
Getting a 1 through a 6.
1 through 6.
Good. 1 through 6 of the possible outcomes. We know the probability for each one of those outcomes is 1 out of 6, right? The only problem is we don't know which outcome is going to occur because that is a random event. That is a random event that we have not done yet. Does everybody understand that? That's why it's called a random variable. The variable has a certain value that it's going to take on. We just haven't did it yet, right? So there are two types of random variables. Just like there are two types of numeric variables, there are two types of random variables. There is the discrete random variable, right? There's a discrete, and then a discrete random variable is counted. So that means that your numbers have to be whole numbers. So this means when it's discrete, this just means that it has to be a whole number. That's all this means, all right? The other variable, a continuous random variable, is a measurable variable, right? And there's a difference in the way we go about doing these. These are measurable. And by measurable, generally that means you can apply a unit to it. And that means that it can be parts, right? And all this really means is that, so when we talk about a random variable, first off, I think I skipped over this. When we talk about a random variable, we define every random variable with a capital letter, and generally use the letter X. So like this, for instance, the number of X, the next 3 customers entering a store who will make a purchase. So we let X be the next three customers entering a store who make a purchase. I'm interested in, here are my possible outcomes for X. If I look at the next 3 customers that'll make a purchase, I can have the minimum number that makes a purchase will be 0. That means nobody made a purchase out of those 3 customers. Then I can have 1 person make a purchase, or 2 people make a purchase, or 3 people make a purchase, right? And we can give probabilities, we can assign a probability to each one of those outcomes. The number Y, capital Y, of 4 patients taking a new antibiotic drug. We can have 0 people taking a drug, 1, 2, 3, or 4. Those are the possible outcomes. We can assign probabilities to those. The size Z of displacement of waste by a manufacturing company in a year. So here, your Z is not, it's not possible to count that amount because it's a size, right? And when we talk about a continuous variable, so here's the difference. These first 2 are what we call discrete, and we can list out their possible outcomes like this. In a continuous variable, you can't list out the possible outcomes. So we use a formula to calculate things. So here we can list out possible outcomes, and we will list out possible outcomes. And we list them out in a table. So list out all the possible outcomes in a table for this particular variable. And this variable over here, when it's continuous, we define it using a formula. And you may also see, this is what we call a density curve. It's called a density curve. So we'll talk about curves too, eventually. So we have 2 types of variables, discrete, continuous, just like we have 2 types of quantitative variables to begin with, they're discrete and continuous. So random variables pretty much follow the same rules as quantitative variables, right? All right, so let's classify each of the following random variables as being discrete or continuous, all right? So X equals the number of girls born to a couple who will have 3 children. So I've defined X as the number of girls born to a couple who will have 3 children. What are the possible outcomes of X? Can anybody tell me that? If you decide to have 3 children, you look at the number of girls that are born. What are your possible outcomes between the 3 children? Anybody? Anybody?
2.
Keep going. What else? What does 2 mean? If you say X equals 2, what does that mean?
X could equal 1 or 2 or 3 in this because you have a 50-50 shot of having a girl or a boy.
So you can have, so let's talk about this. X can equal 1, 2, or 3. Can X equal 0?
Yes.
Let's look at what it's saying. It says the number of girls born to a couple, right? Who have 3 children. So first off, the minimum number of girls that can be born to a couple who have 3 children is going to be what?
1.
Try it again.
0.
0.
Oh,
What does 0
0.
mean? What does 0 mean? 0 means that they were all what? All 3 children were
Boys.
Boys.
right? Do you understand that? The maximum number of children the maximum number of girls that can be born is 3.
3.
It means that you had all 3 girls, right? So your possible values for X here, X will equal 0, 1, 2, 3. Can you have a partial girl? Yes or no?
No.
No. So that means that this is this a discrete variable or a continuous variable? Well, because you have to be a whole number in this particular distribution, that's what we call discrete. That's a discrete variable. Next one. X equals the number of defects found on an automobile at final inspection. The number of defects found on an automobile at final inspection. So on this particular thing, can you have a partial defect or a whole, or does it have to be a whole defect when you're counting it?
You could have a partial defect, like part of
But if it's a partial defect, that means that it's really what?
a defect.
It's still a defect. So it's still a whole defect, is what I'm saying, right? I shouldn't have said partial there. So it's really a whole defect. And in this particular case, it's either a defect or it's not a defect. Even if it's a partial defect, it's still a defect, right? And the key that I want you to pick up on is this is also a discrete variable. This is also a discrete variable, right? And look at what both these have said so far. It says the number, right? And then we see that for both those, the number means that it has to be some whole number. It has to be some whole number that I'm talking about, all right? Look at the next one, the weight in ounces of the sandwich meat placed on a submarine sandwich. Key thing here is that I'm telling you to measure something in ounces. That is a unit of measurement. Because it's a unit of measurement, the sandwich meat that you place does not have to be a whole number. It can be partial or it can be parts. It can be decimals. It can be fractional parts. So this is what we call a continuous variable. And in a continuous variable, you can't list out the outcomes. On this previous up here, we can list out the number of possible defects there are, right? There's not going to be an infinite number of defects on this particular car. The car only has a certain amount of, the car is made up of a certain amount of parts to begin with. So even if every part is looked at, it won't have an infinite number. Here, you can keep breaking this into intervals or parts. That's what this is saying. X equals the number of incorrect lab procedures conducted at a hospital during a particular week. Key thing here again is, look what it says in the beginning. It says the number. And those lab procedures, they have to be whole numbers. So this means that this is going to be a discrete variable again. The time needed by a clerk to complete a task. So when you say the time needed, right, this is going to be continuous, good. This is a continuous variable because time is a unit of measurement. You're measuring something. And the last part says the temperature of a pizza oven at a particular time. Temperature is also a unit of measurement. So this is going to be, somebody help me out. What is this one going to be?
Continuous.
This is also continuous, good. So here's why this matters. It matters now because we treat these variables differently in the way we set them up. And again, I already told you, these are made through tables. Discrete variables, we look at tables. Continuous variables, we look at formulas. On this test, your variables are all going to be discrete. They're always going to be discrete when we talk about our variables so far on the second test, right? So when we talk about discrete, we're going to talk about a particular distribution, and we'll get there in a second. But we start out with what we call a probability distribution. And a probability distribution is just a table or graph or formula. It's a formula that's continuous, but it's a table or graph. It's really a table if it's discrete. That gives the probability associated with each possible value that the random variable can assume. For a discrete probability distribution, the random variable is denoted as X. We call the actual values that X can, the actual values that you can assume, we call those X. So we'll define the variable and we'll say let X equal something. For instance, let X equal the number of girls born to a couple who has 3 children. We've defined X as the number of girls born to a couple that has 3 children. And then we have what's denoted as the probability of X, P of X. That means I'm going to say that for each one of these probabilities, we have an associated probability with it. Same rules from probability apply to a random variable or to a probability distribution. The same rules and probability apply. And here's what they are. This first one is what we call the non-negative probability, the non-negative rule. It says that every probability within this distribution has to fall between 0 and 1. So this is just my non-negative probability rule. This is the non-negative rule, which means that you can't have any negative probabilities. There's no such thing as a negative probability. There's also no such thing as a probability bigger than 1. Every probability must fall between 0 and 1. The other one is that the sum of all probabilities in the distribution is 1. So when we add up the sum of every probability of X, when we add them all up, they have to equal 1. They have to equal 1. So everything has to add up to 1 here, has to sum to 1. Same rules we came up with in probability to begin with, they also hold for a probability distribution. So we're going to verify those rules when we go through this. 2 rules we have to check when we're only checking about probability. We don't care about the X values themselves. We only care about probabilities, all right? So the following is a probability distribution table for the number of radios sold by a certain company in a typical week. I'm defining X as the number of radios sold right here. X is equal to the number of radios sold. So what does X equals 0 mean? That means I've sold how many radios that particular week?
None.
Thank you, 0 radios. What does X equal 5 mean? That means I sold how many radios that particular week? 5, right?
5.
Now, I've given you all these probabilities here, and I want you to find the probability that 2 radios are so. So we're going to write these statements first. And in these statements, we're going to say this is the probability that x equals 2. The probability that x equals 2. I've already defined x as the number of radios sold. So when I say x equals 2, what am I saying? The number of radios sold is 2. The number of radios sold is 2. That's what I'm telling you right now. But when I go to the table, there's a question mark sitting at 2. I can't do this, right? Can I do it? Somebody help
No,
me. Can I
because
do it?
there's no information.
Well, is there enough information to find what 2 is? Yes or no? What do we know?
Yes.
What do we know? Good. What do we know?
The combined probabilities of every other
All
number.
these have to
except
add up to
2.
what number? What do these have to add up
1.
to? 1. They have to sum to 1. So
So it
these
should
must
be-
sum. These must sum to 1, right? Well, how much do I have right now? 0.3, 0.03, that's 0.23, 0.43,
50.
point. Thank you. So this is 50%, right?
Uh-huh.
50% already in the table. So how much is missing then?
50%.
50%, right? So this is just 0.50. If you add them all up, they should add up to what number now?
1.
So let's make sure. 0.3, 0.23, 0.73, 0.93, 0.98, 1.00. So I've given enough information here to actually find what that value of 2 is. And then that value of 2 is equal to 0.50, right? Now, another question. When I look at this particular table, then, let me ask you a question. If I ask you, what do you think is a typical number of radios sold in a week? What do you think is a typical number of radios sold in a week? Anybody give me an answer for that? What is the typical number of radios sold in a week? Or a better way of saying typical, let me say it like this. What is an average number of radios sold in a week?
2,
Why do you say 2?
because 50% of them were 2.
So it looks like the highest probability is sitting at where? 2. That's what we're going to say right here. So the highest probability is sitting at 2. Now, in a second, I'm going to show you how to calculate the actual average for this. But on average, it looks like we're selling about 2 radios per week. So the next one says the probability that at least 2 radios are sold. How is that different from the probability that 2 radios are sold? What does at least 2 radios sold mean?
It could
2 or
include
more.
3, 4,
It can be
and 5.
it can be 3, 4, or 5. So that means I need to add up everything from 2 to 5, right? How do I say that? How do I write that in terms of a statement? That's the probability that x is what? At
Greater
least.
than
What
or
is at
equal
least?
to 2.
Good. Greater than or equal to 2 here. And so that means I'm looking at all of these radios right here. That's the probability that x is greater than or equal to 2. One way to do that is to add up these right here. So that's 0.7, 0.75, 0.78, right? Or 0.77. That's 0.77 if you add all those up. Another way, and maybe even a quicker way, and it'll help you out in the future, is instead of doing it like that, you could also do, it's also equal to 1 minus the probability that x is less than or equal to 1. Can anybody tell me why that's true? Anybody tell me what that statement is saying? Why does that work?
It's basically subtracting the other numbers that aren't considered as a part of it from 1.
Good. Let's look at it like this. We're going to look at it at the number 2. There's a left and a right side of 2. Does everybody see that? If I go to the right of 2, what number's on the right of 2? 2, 3, 4, 5. That's the numbers I want, right? There are also numbers to the left of 2, 0 and 1. I know that every number together has to add up to what number? They ought to be 1, right? So this is called the complement. I'm using the complement. And that we talked about in probability 2. That was using the prime or the C. This 1 says the entire thing adds up to 1. If I want to find greater than or equal to 2, I can just subtract off everything to the left of 2. That'll give me everything from 2 to the right. So this greater than or equal to 2 actually means 1 minus the probability that x is less than or equal to what numbers to the left of 2? What numbers to the left of 2?
0 and 1.
0 and 1. So that's less than or equal to 1. If you do that, then this is the same thing as saying 1 minus 0.23, which is also 0.77. It's also 0.77. That is another way to do that. I'm going to show you that way right now because eventually you're going to have to use that method when we go to Excel to calculate things for a different distribution. Last one says the probability that at most 2 radios are sold. How is that different? At most 2. What am I asking you to find there?
X is less than or equal to 2.
Good. So that's the probability that x is less than or equal to 2. That would be these right here. Adding those up again, it's 0.73. So this is the probability that x is less than or equal to 2. So I want to make sure we understand what the words, and we have 2 words I'm introducing you to. At most, the word at most means less than or equal. The word at least means greater than or equal. Those are the symbols I want you to understand there. At least and at most. All right. Anybody got any questions on this first part? How to read this table? Okay with that? Can anybody else not hear me? Are y'all there? Can y'all hear me?
Hear you.
Okay.
I can hear you fine.
All right. Eric, you might want to log out and come back in. She can't hear me say that because she just said she can't hear me. Hold on. All right. Let's go to the next one then. So now we're going to talk about the mean of a random variable, the mean. And when I said mean, I asked you earlier, what was the typical number of radios sold? Or the average number of radios sold? The mean is the expected value. What are you expecting to get when you do a certain activity? What are you expecting to get when you do something over a long period of time, right? So the mean of a random variable is also called the expected value. And it's written like this. We call the expected value E of x, also known as mu of x. To find the expected value, you multiply the outcomes by the probabilities and sum all of these up. So the formula for mu of x, or E of x, here's the formula. Here's the formula for the expected value, what you're expected to get, or what your average is supposed to be. And all it says is you take every x and you multiply by its probability. In real life, we call this a weighted average. This is just a weighted average. You calculate weighted averages all the time. If you want to calculate your grade in this class, for instance, your grade is made up of 3 components. It's made up of a test component, a homework component, and a final component, right? Test component, homework component, final component. Your test is 60%, your homework is 20%, your final is 20%. I don't think that's right, but let's say they are. The percentages all add up to 100%, right? You take each percent and multiply it by your score, and you will add them all up, and they'll give you your final grade in the class. That same concept is being applied to this right here, except your percentages now are going to be your probabilities. You're going to take your probability and multiply it by, instead of your score now, your score is going to be your X value. So if we look at the expected number of radios sold in a week, right? Look at the expected number of radios sold in a week. Let's come back here. We have all of these X values right here. We can see from the distribution that we're expecting to sell about 2 radios a week, which means that my expected value should come around that number as well. And that's because you have the highest probability sitting at 2. Here's how we calculate it. We're going to take every X and multiply by its probability. So the expected of X also called the mean of x, mu of x, is equal to, you take 0 and you multiply it by its probability like this. Then you're going to add the next one. You take 1, multiply it by its probability. Then you're going to add the next one. You take 2, multiply it by its probability. You're going to add all of these down here like this, right? I'm not going to write all those out. But that's plus point. The last one would be 5. The last one would be 5 times 0.02. Okay, this is just me showing that I'm skipping 3 and 4 in a sequence, but those will be added up to, right? So all we gotta do is plug these into some kind of calculator, figure out what they are, and add them all up. We'll get our answers. Everybody understand that? So we're gonna go to Excel and do this in Excel. We're gonna do this in Excel. All right. So if you have Excel open, I don't even know if I have Excel on my iPad anymore. All we're gonna do is we're gonna make 2 columns. We're gonna make 2 columns here. We're gonna make an X column. So what are my X's? And then what are my probabilities, my P of X's? There. So my X's were 0, 1, 2, 3, 4, and 5. There are my X's, 0, 1, 2, 3, 4, and 5. Probabilities, 0.03. Can somebody call them out? Tell me real quick. I don't remember what they were. I don't want to keep switching back and forth.
0.20,
Thank you. What's the next one?
0.50,
Hold on 1 second. All right, what's the next one?
0.20,
All right, next one.
0.05, and 0.02.
Thank you. Appreciate that. So, yep. So here are your X's, right? Here's how this works. What I want to do is I want to multiply every X by its probability and then sum them all up. All right. So in this next one, all I'm going to do, I'm going to multiply every X by its probability. So here I'll do, using a formula here, just multiply this column, A2, times this column, B1, not B1, B2. That's that value. 0 times 0.03 is 0, by the way, right? I'm just going to drag that down to encompass all of those. That did not do what I wanted it to do. There. I'm struggling. And it still didn't feel it. Anyway, hold on. I gotta do this for every one of them. I am definitely going to my computer in a second. This time that. Hey, if you're on your computer, you should be able to drag and fill. Mine isn't letting me do it for some reason. I'm sure there's a way to do it. I just
Is this
need to
one of the
figure out.
times where you have to put like the $sign in front of it?
Nah, it's just that I'm on my iPad right now because I didn't want. I was being lazy because I didn't want to switch between both of them. I should have just did it on my computer. If I'd have dragged, it would have worked. There go all your probabilities multiplied by their X values, though. There go all your probabilities multiplied by their X values. And this is actually easier calculations to make. You're just doing, like, for instance, 0 times 0.3 is 0. 1 times 0.2 is 0.2. 2 times 0.5 is 1. See what I'm saying? 3 times 0.2 is 0.6. So now the last thing I'm going to do, though, is I want to add all these values up. So this right here was every X times the probability of X. That's what that is. That's every X times the probability of X. The last thing I want to do is I want to sum those up. So this equals, I'm going to use the sum function right here, your sum function. Drag down. Sum, almost, there we go. Sum those values. I don't know what this is. Oh, there you go. So sum those values up. Here's what I get. I get 2.1. So the average number of radios sold in a week is 2.1. And it should kind of make sense that the average is 2.1. We know the average should be around 2 because at 2, we had the highest probability. 2 had the highest probability. So we'd expect the average number to be around that number 2. And this is the mathematical average. And what this really means is that if we look at this particular store that sells these radios over a long period of time, over the long run of time, then on average, you're going to sell about 2.1 radios. Can you really sell 2.1 radios? Yes or no? Can we
No.
sell 2.1 radios? No, why not?
They're not selling
Because
partial
it has to be a
radios.
whole
Good, it
number.
has to be a whole number. But mathematically, the average is 2.1 here. All right. So here. Vector of X is 2.1. So I can grab that. Paste that in here. There we go. That's nice. There's your expected. Any questions on how to find the expected value, the average so far? The average is literally taking every X and multiplying it by its probability, all right? And once you do all that, you're going to add them all up. You add them all up, all right? That's how we get that value of 2.1. You should write that. This is the sum. That's how we got the sum. All right. So you try this example here. Insurance companies use expected values to set their premiums for customers. Imagine the following scenario. An insurance company sells $20,000 whole life insurance policies for annual premiums of $300. Actuarial tables show that a person who would be sold such a policy with this premium has a 1 in 1,000 chance of death during a year. Let X be the random variable representing the profit the company can make on one of these policies in a year. Find the expected profit for the company. Break this down. I already gave you all the information. I also made the table for you. If I wouldn't give you this table, let's talk about this real quick. It's a real life example. Insurance companies, they make money based off the fact that you might do something, that something might occur, right? So when we look at this, X equals the profit the company is going to make. And for every profit, there's a probability. So here's how this works. In order to get a policy, you have to pay $300 premium. So the profit that the company is going to make is at $300, right? And then the money they're going to lose is if some kind of accident happens, or basically if somebody dies, they're gonna have to pay $20,000 to that person if they die, or to that person's family if they die, right? So your possible X's for profit are $300 for every premium you sell, for every life insurance policy you sell, and then there's a negative $20,000 if somebody dies. So that's what this sets up as first. Here are your possible X's: 300, negative 20,000. This if the person lives, this if the person dies, right? Everybody got that part first?
Yes.
Now, there is a 1 in 1,000 chance that a person dies. Not a very high chance of a person dying. So the probability of a person dies is 1 in 1,000. The probability they live is the complement of that. 999 out of 1,000, right? That's what this says. So if you want to, we can call these decimals, by the way. This is the decimal point 999, it's the decimal point 001. If I want to calculate the expected value, how would I calculate my expected value? What would I do? Anybody want to take a shot at this one? How do I calculate the expected of X, also known as the mean of X? How would I calculate that?
Multiply 300 by 0.999.
Good, so that's the first part, 300 times 0.999, that's a person living. And we're gonna add what to that? Or in this case, we're really gonna do what? We're not gonna add, we're actually gonna do what?
Subtract 20,000
Subtract.
point
Good,
zero
so we're gonna
zero one.
subtract here, so it'll be minus, because you have a minus sitting here. That's a minus. So we're gonna minus 20,000 times 0.001. So this is just doing some math. You can do this in Excel. I'm gonna do this in a calculator right here. 300 times 0.999. 299.7 minus 20,000 times 0.001 minus $20. So it's 299.7 minus $20. That is 279.7. So this is how much money they're expected to make off of one person living, right? So this is their average profit off of one person. We know insurance companies have thousands and hundreds of thousands of people they're making off of those people right there. That's why it's so hard to get your money when an accident actually occurs. It's like an act of Congress to get your money when an accident actually occurs. So they don't want to give up any of it, but they make that much off of it, right? And that's how you calculate the expected value. So they make $279.70 off of every person. If you have a lot of people, it's going to be a lot of money. But do we understand how to calculate the expected value? Yes, everybody okay with that, right?
Yes.
All right, good. So now let's move on then. If we can calculate expected value, we can also calculate this thing we call the standard deviation. And I want you to remember what the standard deviation is. The standard deviation is the average deviation away from the mean. The average deviation away from the mean. So let's say we're supposed to sell 2.1 radios in a week. Supposed to sell 2.1 radios in a week, right? If we're supposed to sell 2.1 radios in a week, how far will I deviate from that on average? That's what I want to know now. How far will I deviate on average from that number, right? And all we have to do to calculate that is, here's the formula. It says do X minus the mean. X minus the mean. What is our mean for this particular problem, by the way? Can somebody remind what that was? What was the expected
2.1.
mu? 2.1. So my mu here is 2.1 radios, right? This says to take what first? This says to do every X and subtract it from what? What number? 2.1, right? Whatever that value is, I'm going to square it. After I square it, I'm going to multiply by its probability, and I'm going to add all those up. I want to find, that's called the variance. This is what we call, this is called sigma squared. That's sigma squared X, that's the variance. I actually want to find, though, sigma X, which is the square root of the sum of the P times the I, X minus mu squared. That's what I want to find, standard deviation. So sigma X is the standard deviation. This is the standard deviation, in case you were wondering. This right here is the variance. That's what we call the variance. All right, to get to the standard deviation, we have to find the variance first, generally speaking. Now, we already found our mean for this particular problem. So here's how this sets up. We're going to take every X. So to find sigma X is equal to the square root of. Take every X and subtract it from the mean. So I'm going to do 0 minus 2.1 squared. And I'm going to multiply that by its probability, which is 0.03, plus 1 minus 2.1 squared. And I'm going to multiply that by its probability, which is 0.20, plus 2 minus 2.1 squared. Multiply that probability, which is 0.50, plus all the way down to the very last value, which is 5 minus 2.1 squared times probability, which is 0.02. And I'm going to take the square root of all of this stuff right here. And I'll get my standard deviation, right? So we're not going to calculate this by hand. We're going to go to Excel and do this. I think I'll try to do this one on my, I want to do it on my iPad still. Just got to figure out how to drag and drop. So let's go ahead and try this one again. Figure it out. So the first thing I'm going to do is I'm going to calculate my deviations. By that I mean I'm going to calculate every x minus the mean. So this first column is going to be x minus 2.1. I'm actually going to just square that. I'm going to call that column, let me call it this. I'm going to call that column deviations. Deviation squared. So I'm going to call it deviation squared. So all it is I'm going to take every x, put in parentheses every x minus 2.1. If you're doing this on your computer, you can actually just grab this value down here if you want to. Minus 2.1. And you're going to square this. Where's my square button? There, square it like this. Deviation squared. There. If you do it on your computer, I think you will have to actually use the $ to lock it, because it'll keep doing it if you don't. There's got to be a way to do this. Wait. Bill. Oh yeah. That did not fill it what I want to fill it with, but that filled it with something. Oh, and again, that's because I don't have the $ in front of my thing. That's why mine messed up. So I needed to put the $ in front of C8. Is it the $ or the ampersand? It's the $, right?
Yeah, it's a $sign.
Thanks. I know y'all probably like, why he just don't go to the computer right now? I'm struggling. God, this is no fun, man. There. Y'all get these values? Y'all got those values, right?
Yes.
Cool. Those are your deviation squared. So that's every x minus 2.1 squared. Everybody got that? That's every x minus 2.1 squared. Here, I'm going to take every one of those values and multiply them by their probabilities. So I'm going to multiply everything in E1 by the probability in the next one over there. So equals this times the probability here. There. And we want to drag. Yeah, we want to drag. Anyway, just write them all out. Equals this times this. Ah, I messed that up. There we go. Equals this times this. There we go. So here are all of the deviations multiplied by their probabilities. So this is basically everything in, I'll write it out. I'm not gonna write deviation squared, but that is everything in E1 times every P of X. There. So everything in E1 times P of X. And the last thing is, I wanna add them all up. So I'm gonna go to sum. And I want sum of all of these numbers. There we go. There you go. Here is the standard deviation, 0.89. Now, I'm almost certain there's a quicker way to do this. There's got to be a quicker way to do this. I'm going to try to find it in a second. But the deviation squared is equal. So here's what that 0.89 represents. That 0.89 is the variance. That 0.89 right now is the variance. If I want the standard deviation, this right here is the variance. That is sigma squared x. That's the variance. If I want the standard deviation, what do I have to do? Anybody tell what I got to do to find the standard deviation?
You should take the square root.
Good. So we take the square root of that. Square root of that number, and I get this right here. There is the standard deviation. So the average deviation from 2.1 radios sold is 0.943 radios. That's what this is saying. The average deviation. So we're going to vary on average from 2.1 radios. The expected number is 0.94 radios sold. That's what this is saying right here, right? Copy. Let's go bring that over and put that over here. There we go. That's what we get. So sigma squared x is equal to 0.89. 0.89, and sigma x is equal to the square root of 0.89, which is 0.943. So the average deviation from the mean, which in this case is 2.1, the mean, which is 2.1, is 0.943. What that really means is that we wouldn't be surprised if in any given day we sold 2.1, so it means 0.943 is about 1 radio. So you wouldn't be surprised if you only sold 1, that'd be a typical day 2, or you sold 3, that would be typical. That's how you use the standard deviation there. Standard deviation is calculated like that. Standard deviation is a little bit more work, but it's not a hard calculation to do. The only thing you need to remember is when you do the standard deviation though, you're going to multiply, you're going to subtract the x from the mean first and then square it. Subtract the x from the mean and then square it, and then multiply by its probability. But both these things follow the same process. They're both multiplying an x by a probability and then summing up. All right. Any questions on that? You okay with that?
Yes.
All right, cool. So that is what we call probability distributions now. Now I'm about to get into a very specific distribution. And it's called a discrete distribution known as the binomial distribution, all right? So for this particular set of notes, I'm going to add in other notes, though, all right? I'm going to add in another set. So if you didn't get the other set that's on Blackboard, make sure you get the other set on Blackboard called the binomial notes. Let me go bring those in. That would be a file. That would be in my G drive. So we're going to talk about the binomial distribution, all right? And in a binomial distribution, first I will start off by breaking this word down. Bi. What does the word bi mean? Anybody tell me what that word means?
2.
2.
2. So here we have the root. We have the prefix bi. Bi meaning 2. It's a known meaning name, so it's 2 name distribution is what we're saying here, right? So it's the 2 name distribution. So this word bi means 2. So when we talk about things, that
Did
means
you
2.
add it to the chat box?
I can. I'm sorry.
Please.
Let me do that for you. All right. So again, binomial means 2 name distribution. All right. And this is a discrete distribution. All right. The objective is to identify the characteristics of a binomial, find the mean and standard deviation, and then calculate binomial probabilities. So this particular distribution is what we call a discrete distribution. It's called a discrete distribution. Discrete meaning what again? What does discrete mean?
Numerical.
Keep going.
Whole number.
Whole number. So everything in this distribution has to take on a whole number. Every probability is associated with a whole number. All right. And so here's an example. You've just been given a surprise multiple choice test that consists of 12 questions. Each question has 5 possible answers. Because you know very little about the test, you have decided to randomly guess on each of the 12 questions. We're going to find these following probabilities. If you are totally guessing, how many are you expected to get right? If you guess exactly guessing exactly 5 questions right, find the probability of guessing at most 5 questions right, and find the probability of guessing at least 5 questions right. So let's talk about this real quick. You take a 12-question test, right? You're guessing on the entire test. You have no clue what's going on. There are 5 answer choices for each particular question. My first question is this. What is the probability that you get any one question correct? Can anybody tell me that? Can anybody tell me that?
20%.
What's the probability I get? Say it again.
20%.
Why 20%? That is correct. Why 20%?
Because your one correct answer or your answer choice is one selection out of the 5 possible answers.
Good job.
So
Good
it's
job.
20%.
So the probability we get any one question correct is 1 out of 5. And we're going to call that, if you get it correct, we're going to call it a success. So let's do this real quick. Let's define a random variable x. Let's let x equal the number of correct questions. The number of correct questions you get on this test. Question number 1 is this for me. I need you to answer this question for me. Is x going to be a discrete random variable or a continuous random variable? Is x going to be discrete or continuous? Why is it discrete?
Because you can only get one right or one wrong. You can't get half of one. Or
you can only get whole numbers here, right? We can only get whole numbers here, right? There are no partial getting correct. Either you get it right or you get it wrong. Good job. So this is going to be a discrete random variable we're talking about. Now, what is the probability? Let's start here. We just said that getting any one question correct, that probability is going to be 1 out of 5. We're going to call the probability of any success then. We're going to use a new variable, and I'm going to call it this variable here. I'm going to call it pi. The Greek letter pi. Pi just means you got a successful question. The probability of getting any question correct. This is 1 out of 5, or that's equal to 20%. If pi is equal to 20%, I hate using pi. I like using letter P, but your book uses pi. I think the homework uses pi too. If pi is 20%, that is a correct answer. That is a correct question. What is going to be failure? What is failure here? Let's let pi be success. You got it correct. What is failure? You got it wrong. What's the chance you get it wrong then?
4/5.
Which is good. So we'll say that this is 1 minus pi. That's what we're going to say there. We're also going to call that, I'm going to call it Q right now. 1 minus pi is Q. They're the same things to me. But 1 minus pi is 4/5 or 80%. So there's a 20% chance I get any one question correct, but there's an 80% chance I get any one question wrong. The odds are not in my favor right now to begin with. Is everybody understand that, right? Now, if I'm randomly guessing on this test, better question is this. Next question is, how many questions am I going to take? How many questions am I going to guess for on this test?
12.
I want to guess for 12 questions. Can I take more? Can I do more than 12 questions? No, there's only 12 questions. I'm going to guess all 12 of them, all right? So that number is not going to change. That number is fixed. That's what we say there, all right? And if I'm randomly guessing, if I get the first question correct, does that affect me get the second question correct? Yes or no? If you're randomly guessing,
No.
will that affect you getting the next question correct? Well, if I get the first question correct, does that affect me getting the last question correct? Yes or no? Somebody just said it was no, right? And they might tell me what that concept is I'm trying to build right there, where no one question affects the next question or the other questions.
Independent.
What am I trying to tell you? They're independent. Good job. They're independent. Do you remember what it means to be independent in probability? If things are independent in probability, what does that mean?
One thing
What can we do?
On,
You're right, but what can we do? What can we do to your probabilities that are independent? Do you remember? If two probabilities are independent, what can you do to them?
Is this where like the probability of this given this equals the probability?
That's close. That's conditional probability. That's too far. I just want the basic assumption of independence. The basic assumption says that if two things are independent, you can multiply probabilities. That's what the basic assumption says. So if two things are independent, we can literally multiply the probabilities. So my question is this. Let's start off with a simple question. What is the probability that I get all 12 questions correct? Can anybody answer that?
Wouldn't you multiply 12 times 0.2?
You are close.
Oh.
You said 12 times 0.2. That is close. How many questions am I doing again?
12 times.
12, right? So let's go with this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Here are my 12 questions, right? Here are my 12 questions. If I want to get them all right, what has to be true about every one of those blanks? What number should go on every one of those blanks? They ought to be what number?
5.
The 20%.
Try it again. 20%. What does that mean? This means that every question on here I guess correctly, right? Now, y'all said do 12 times 0.2, right? But what is this actually saying?
0.2 times.
I have 0.2. I have 0.2 how many times?
12 times.
12 times. So this is actually written as 0.2 to the 12. That's 0.2 to the 12. Oh, it's 0.20 raised to the 12th power. That means I got every question correct. Can I calculate that? Well, if they're independent, what do I know I can do between every one of these problems then? I can do what? Because they're independent, I can just multiply them. That's why we're doing this, right? So I can just do 0.2 raised to the 12th power. Here's the probability I get that. It's a very slim chance that I guess every one of those questions correct. As a matter of fact, what's the probability that I get them all wrong? Can you tell me that?
0.8 to the 12th power.
0.8 to the 12th power, right? So let's see what has a greater chance. 0.8 to the 12th. There's a 7% chance I can get them all wrong. There's a much greater chance of me guessing them all wrong than guessing them all correct. But even that is very hard to do. That only happens 7% of the time, right? I'm asking you right now though to find what is the probability of guessing how many? Guessing exactly 5 questions right? Well, I want to guess exactly 5 questions right. What does that mean? How does that change things? How does guessing exactly 5 things?
Would that be 0.2 to the power of 5?
Good job. And then what? You're on to it. Keep going.
plus 0.8 to however many are left after that?
How many are left?
7.
How'd you get that?
12 minus 5.
Good job. Hang on to that. Hang on to that. We got further than I was hoping to go right there, and y'all did a great job of doing that, by the way. That really surprised me. That sent goosebumps down my spine. Good job. So what I'm telling you then, what you already picked up on is we need to have this 0.2 how many times?
At least 5.
5 times here for this particular problem. 5 times here, which means that the rest of these have to be what? The rest of these have to all be 0.8s, right? And how many 0.8s am I going to have then?
7.
7.
Somebody says 7 because they just did 12 minus 5, right? What you really have just did, by the way, is you developed the binomial formula, the binomial distribution. You've developed the binomial distribution. Can anybody tell me why you think it's called the binomial distribution? What does the word bi mean again?
Bi means
Go
2.
ahead. 2. So somebody just was about to say there's 2 what?
There's 2
There's 2
parts
what?
to the equation.
2 parts. There's 2 outcomes, actually. What are the 2 outcomes here? Either you get it what?
Right or
Right.
wrong?
You get it right or you get it wrong. Everybody got that?
Yep.
There are only 2 outcomes, success or failure. Success, we're going to define it as pi. You may even see it written as p. I use p a lot. I'm in the habit of p. Failure is 1 minus pi. So failure, if success is 20%, 1 minus 20% is your 80%. We're going to call that q. All right. Now, the problem with setting it up exactly 5 like this, what's wrong with this? Exactly 5 questions right. Well, this says I get which 5 questions right? The first 5 questions right. Is that the only way to get exactly 5 questions right?
No.
No, I can get the last 5 questions right if I wanted to, right? Which means that these will all be wrong in the front of them. Does everybody understand that? As a matter of fact, how many ways can I get 5 questions right in a 12-question test? That's my real question now. How many ways can I get 5 questions right in a 12-question test? Anybody want to take a shot at that?
5 out of 7.
Isn't it like the factorials?
That is correct. It is the factorials. Y'all are saying it right. Somebody said 5 out of 7. I think what you really mean is the factorial 5 out of 7, right? It's kind of more of a, how many things do we have set here? How many different questions do we have? How many questions do we have? 12. And how many do I want to get right?
5.
How many do I want to? I want to choose 5 to be right. So really, what this is going to break down to is then we're going to look at 12C5. 12C5 gives me the number of combinations I can have for 5 questions being right. Then y'all tell me that we have 0.2 raised to the 5th power, and we have 0.8 raised to the 7th power. And this will give me the actual first one for this one right here. This will actually calculate this value right here, guessing exactly 5 questions right. And I'll show you that in a second. But this is the formula, and you've already developed it. I'm gonna formalize it in a second more, but this is the formula to actually get that answer there. All right. So let's go and look at the properties of a binomial distribution. In a binomial experiment, the binomial distribution itself is debatable. We call it a binomial experiment. In a binomial experiment, there are only 2 outcomes. They can be classified as success or failure. Success is denoted as pi. So success in our case was pi equals 0.2. Failure is denoted as 1 minus pi. Failure in our case was 0.8, 1 minus 0.2. There are what we call a fixed number of trials, which we're going to refer to as n. For the particular example we just did, our fixed number, the number you cannot go past, the number you have to stop at, n was equal to 12. N was equal to 12. And each trial is independent of the last trial. Because trials are independent of each other, we can multiply probabilities. It should be multiplied, not multiple. We can multiply probabilities. And the last thing about a binomial distribution is that the probability of success is fixed or constant, which means it doesn't change from problem to problem. So when you're guessing on a test, your probability of getting something right isn't going to change from problem to problem. All right. So there are 4 properties. 1, first property, 2 outcomes, success and failure. Second property, fixed number of outcomes. We call that N. Third property, each trial is independent. The independence allows us to multiply probabilities. Fourth property, probabilities aren't going to change from problem to problem or from thing to thing. So to find the expected number, which was the first question I asked you, what is the expected number here? All right. Let me give you a very simple, we call a very simple binomial experiment or binomial experiment in this case. Let's flip a coin. If we flip a coin, and I want to let X equal the number of heads when I flip a coin. The number of heads when I flip this coin, right? And here's what I'm going to tell you. I'm going to tell you that when I flip this coin, I'm flipping it 100 times. I'm flipping it 100 times. How many heads am I expected to get? Anybody tell me that? Flip a coin 100 times. How many heads am I expected to get? Can anybody tell me that?
50.
50. Why?
Because you have 2 outcomes.
Which are what? What
Heads
are 2
or
outcomes? Heads or tails? Which one is success?
Heads,
Heads. Which one is failure?
tails.
What's the probability of success here? What will my pi be? What's my pi?
50.
50%, 0.5. What's my probability of failure? What's my 1 minus pi?
0.5.
It's also what? It's also 0.5. I understand that. So look, first condition, the first condition for a binomial is met. We have 2 outcomes, success and failure. Second condition, how many times are we flipping that coin? How many times are we flipping that coin? 100 times. Will we go past 100? Yes or no?
No.
So we are fixed at 100. Second condition is met. Third condition. Are the trials independent of each other? Will one flip affect the next flip? Yes or no?
No.
No, so they're independent. So we can multiply probabilities. Fourth condition. Does the probability of landing a head or a tail change from flip to flip?
No.
No.
No, it stays condition. So look, I want you to understand right now, this is a binomial experiment that we're looking at, a simple one. And you're able to tell me off top that the expected number of heads you're supposed to get is 50 heads, right?
Mhm.
So let's go ahead and develop this now to what we were doing a second ago. So for our multiple choice test with 12 questions, each with 5 possible answers, if you are totally guessing, how many you are expected to get right? We define every binomial experiment based off of 2 parameters. The parameters are what we call our true value. So these are the parameter notation here. It's what we call we say that we're talking about the true values or the population values. This is what we call our population value. Talking about the population values. It's defined based on 2 things. If I know these 2 things, I know everything about the binomial. The notation reads like this. We say the random variable X, this symbol means follows. It means follows. So X follows. The B means binomial. X follows a binomial distribution with 2 parameters, the fixed number N and the probability of success pi. Those are the 2 parameters of the binomial. If you know those 2 parameters, you know everything about the binomial. For instance, if I know my N is 100, my probability of success is 0.5, then I can find the expected number, E of X or mu of X, by calculating N times pi. 100 times 0.5 is 50. If we're doing it for our particular multiple choice test with 12 questions, where there's 5 answer choices for each question, only 1 of which is correct, we can first off define it like this. Here's how we define that. Here's how we define the parameters. X follows a binomial with an N of 12. Our fixed number is 12. Our probability of success is 0.20. And then from there, I can tell you that the expected number of successes, the expected number of successes, or the mean of X, is just equal to 12 times 0.2. I'm on average, I'm expected to get 2.4 questions correct. Now, can we actually get 2.4 questions correct? Yes or no? No, because this is a discrete distribution. Numbers have to be whole numbers. But mathematically, the average is 2.4 questions correct. I can find the variance in the standard deviation by doing this. The variance is just n times pi times 1 minus pi. Well, we know that n times pi already is what? What's n times pi? That's already 2.4 for us, right? So the first part is just 2.4. What is 1 minus pi?
1.4.
Try it again. What's 1 minus pi? That might be the right answer. What's 1 minus pi, though? What is pi? Pi is the probability of success, right?
0.5.
So the probability of success is 0.2. What's 1 minus 0.2?
0.8.
0.8. This 1 minus pi is the failure rate. This is just failure. So when we calculate this, this is actually equal to, I'll write it all out for you. This is actually equal to 12 times 0.2 times 0.8, the failure rate. And that means that this part down here is equal to the square root of 12 times 0.2 times 0.8.
Do we square the variance?
No. Good question, but no, don't square it. That square just tells you that you're looking at the variance. The square here tells me I'm looking at the variance. This is just the formula right here. So 12 times 0.2 times 0.8. This is equal to 1.92. Take the square root of that. 1.386. We talk about this value right here. So we're expecting to get 2.4 questions right. That's going to deviate on average by 1.386. We're going to deviate on average by 1.386 questions, which again, you can't have 1.386 questions, but you can look at it in terms of about one question here. But this is how we find the particular, these are actually what we call moments in math, the moments, but this is how you find the mean or the expected value. You just multiply n times pi. Standard deviation, n times pi times 1 minus pi. So that's fixed number times success times failure, and then take the square root. It's a very simple calculation to make. Are there any questions on that? No questions on that, right? This right here, again, is your parameter notation. This tells me the fixed number and the probability of success. Likewise, and conversely, if I know success, I always know failure. Because remember, this is binomial, so there's only two outcomes, success and failure. If I know success is 20%, failure has to be 80%, right? So we already talked about this, and you already developed the formula for me, by the way. You already did that for me. So great job on it. Instead of 12 questions on this test, let's assume there were 3. We've already done that part. We want to know what is the probability of getting exactly 5 questions correct. Here's what we can do then. We can actually create a table, because here are your possible outcomes, right? If x equals, remember we said x was defined as x is equal to the number of correct questions. If x is equal to the number of correct questions, can anybody tell me what x equals 0 is? What does that mean? What does x equals 0 mean?
No question.
That is no question correct. What does x equal 12 mean?
All of the questions correct?
What does x equal 5 mean?
50%.
I mean, you got 5 questions correct. Does everybody understand that? Now, To calculate this then, here's what happens. If I want to find the probability of getting exactly 5 questions correct, we already said that that sets up like this. To get 5 correct, you would have to have probability of success 0.2 how many times? 5 times, right? And then probability of failure 0.8. How many times do you have that? Trying to remind me?
7.
7 times. How do we get the 7 again?
12 minus 5.
12 minus 5, good. But we said that we can, this assumes you get the first 5 right and the last 7 wrong, right? It's not the only way to get 5 right. We said we can change that by using the combination formula, which is, in this case, we're going to take 12 things, combine 5 of them. So here's the actual formula, 12C5 times 0.2 raised to the 5th times 0.8 to the 7th. If I calculate that, 12C5 is equal to this right here, 792 ways. There are 792 ways to get 5 questions correct out of 12 things on this test, by the way. 792 different ways to do that. Multiply that times 0.2 raised to the 5th, and multiply that times 0.8 raised to the 7th. There is a 0.053 chance that you get exactly 5 questions correct. Let's equal to 0.053. Now, if we come back here real quick, I want to develop the binomial formula for you. I'm going to show you how I got this, all right? Binomial formula says this. We're going to let me change my colors. X is binomial with a N. Change that color. N and a P. Right? So X is binomial N and P, where X equals the number of successes. And N equals the fixed number. And P, I don't want P, I want pi. My fault. Pi is the probability of success. And then 1 minus pi equals the probability of failure. Here are all the variables defined for you, all right? They're all the variables defined. X is the number of successes, N is the fixed number, pi is the probability of success, 1 minus pi is the probability of failure. Here's how we write the formula for the binomial. The binomial starts out like this. It's written as N, C, X. What does N stand for again? N is the what?
Fixed number.
Fixed number. And then X is the what? Number of successes, right? NCX. That's how it starts off. So in our case, we had 12 C5. 12 questions. I want to get exactly 5 right. Then we said we had the probability of success is 0.2 raised to the, so we had 0.2. We had 0.2 and we raised that to the what power? We raised 0.2 to what power again? Remind me.
To the 5th.
To the 5th power. So what does that 5 represent again though? That 5 is represented by the
5 correct.
So that's 5 to the X. So that'll be pi raised to the X power. That's what this says. And then we have 1 minus pi. 1 minus pi in our case, which was 0.8, and we raised 0.8 to what number?
7.
The 7th power, right? How do we get that 7? We did the fixed number minus the fixed number in minus the number of successes. This right here is what we call the binomial formula. That is the binomial formula. 12C5 says So 12, C5, 12 things, choose 5 of them. 0.2 raised to the 5th power, right? And then you do the failure rate. So if 0.2 is success, failure is 0.8 raised to the 12 minus 5, which is 7. 12 minus 5, that's 7. That's how we get this formula, right? Now, we already did this problem right here. I did it for you, and I got this number 0.053. We're not going to do this by hand. But you need to know where the form is coming from, where the form is coming from. You may also see it written like this, by the way. 12C5, they'd be written as something like this, too. This also means 12C5. You see it like that, that's 12C5 as well, by the way. They mean the same things. But it's equal to 0.053. I'm going to show you how to use Excel to calculate this now. Because I don't care if you can calculate it by hand, but the combination part is the part that really messes me up. So go into Excel. We're going to use a formula. In Excel, you have the binomial formula. So start typing in the word binomial, B-I-N. You have the binomial distribution, B-I-N-O-M.dist. Binomial distribution does one of two things. It can calculate an exact value for you. Here's how you do it. The number S is your fixed number N. What was our fixed number N? What's our fixed number? Somebody remind me. I'm sorry. Number
12.
S.
12.
I'm sorry. Number S is the number of successes you want. How many successes did we want?
5.
5. So first number is 5. Trials, that's your N. What's my fixed number?
12.
12.
12. Probability S is the probability of success. What's my probability of success?
0.2.
0.2. This last part says cumulative. Cumulative is either going to be true or false. Anybody tell me what the word cumulative means?
If it's
Altogether.
independent or not.
Good, it's all together. I like that word. All together. It means you're adding up all together. Cumulative means you're adding up all together. And what that really means is when you say all together, right? You're adding everything up to a particular number of successes. You're adding everything up to a particular number of successes. Here, we want to know exactly 5. So when we talk about the word exactly, or we talk about the word equal, our cumulative needs to be set to false. So I'm going to type in the word false here. Type in the word false. And what this means is going to calculate the value at exactly 5. Maybe they just want to F. What are you doing? My fault, y'all. Let's see if it calculates this. I didn't like that. There you go. Type in false. So you use the words true and false. If you use the word false means you're using the exact. And in statistics, we have a name for that. We call it the PDF, the probability density function. But Excel says either it's true or it's false for cumulative. So let me come back over here. And for this particular problem, what you're going to do is you're going to do, again, this was binom.dist. We had 5 successes, 12 trials, 0.2 was my success, and this was the word false. And this is finding the probability that X equals 5. So this particular probability right here is 0.053. That's what that says. That one probability is right there. If I wanted to find the probability of 0, what would I do? How would that change this formula to find the probability of 0? Can anybody tell me that? How would I change that formula? What would change in that formula if I want to find the probability X equals 0?
First number.
The first number changes to a what?
0.
What about if I want to do 1? The first number would change to a 1.
1.
What if I want to do 2? This would change to a 2. Now, what's the probability of getting exactly 3 correct? How would I do that then? Exactly 3. What would that be? Again,
That first number
we
would be
write it
3.
like, yeah. So we write it like this: probability x equals 3. X equals 3. And we write that as binomial dot dis. This number is 3. That's 12.2. And again, this is false. The word false means you're doing equals. What's the probability of getting all 12 correct? So it's probability x equals 12. Then we write this as binomial.dis 12, 12.2 false. So all those are going to use the false when you do exactly something, all right? All those use the false. That's what the false tells me. The false says I'm going to calculate at that particular value. Anybody calculated those? Somebody want to calculate it for me? I got it. Thanks, you guys. So here, this first one changes to a 3. 0.0236. So this one was just equal to 0.236. And then here, this first one changes to a 12. We already found that one, by the way, earlier. That's a really small number. 0.79. That looks like this. 2, 3, 4, 5, 6, 7, 8, 4, 1. There you go. It's 8 zeros and then 419. 4, 1. I don't know what the rest of it was. Very small. So these are all exactly. Now, at most and fewer are going to be different then. That's what we're really getting to. On this test and 5 possible answer choices, what's the probability of getting exactly or getting exactly at most 5 questions correct? So I want to get at most 5 questions. I don't like the word, get rid of that. At most 5 questions correct. What does at most 5 mean? I want to tell me what at most 5 means.
That you can get 0, 1, 2, 3, or 4 correct as well.
Good. So that means you can, if you talk about at most 5, let me try to copy this table real quick. Cut this out. There you go. Copy. Paste. There we go. All right. So look, at most 5 here means that it can be all of these values in front of 5, right? This is the probability that x is. What does that really mean in terms of your symbol then? What symbol is that at most?
Less than or equal to 5.
Less than or equal to 5. And that means I'm going to have to add up everything in front of that, right? So that means I have to do binomial dis of 0, of 1, 2, 3, 4, and 5 to get there. Does everybody understand that? I don't want to do that the entire time. There's a much quicker way to do this then. So the probability that x is less than or equal to 5 is actually equal to binomial.dis 5, 12.2, right? 5, 12.2. So number of successes I want. This time I'm doing the number of successes I want to stop at. I want to stop at 5 successes here. I want to stop at 5 successes. 12 questions, 20% chance of success. The last part that I'm going to change it to true. The last one I'm going to change to true. And what that means now is it's going to add up everything in front of where you're stopping at. So I'm going to add up 0, 1, 2, 3, 4, and stopping at 5 and add all those up. So that's how we change the formula to do. This is called a cumulative distribution. This is what we call a cumulative. That's why cumulative is either true or false. We're accumulating now. They're cumulatively adding up, right? So when I go back into Excel this time now, I'm going to change this to a 5 in the front. That's where I'm going to stop at. I'm going to change this back here to true. And here's the probability of getting at most 5 correct. This is at most 5. 0.981. Fewer than 5 questions correct. How is that different? How is fewer than 5 different than at most 5? How is fewer than 5 different than at
It
most 5?
doesn't-
Anybody can tell me that?
Doesn't include
Good.
5.
Good job. So this is x less than 5. Well, in this particular distribution, you have to be at a number. It's discrete. So if I'm less than 5, where am I really at? Where am I stopping it at?
4.
4. When you see something like this with a less than, then that means you're to the left of that number. So this is going to be represented by these numbers here. This is the probability that x is less than 5. If I want to calculate using the Excel or my calculator, though, how do I have to write this? This is the probability that x is less than or equal to 4. So binom dot disk. This time I'm going to stop at 4 successes, 12.2, and again I'm true because I want to add them all up. This is less than 5. Less than 5 really means less than or equal to 4. So I'm going to go back here, and the only thing I'm changing in this formula now, that 5 changes to a 4. Because that means I'm going to add them up to 4. I'm going to do that. 0.927. I get a smaller probability because I've included less into it. And again, it says, what is the difference between these two probabilities? One includes 5. The first one includes 5, the second one doesn't. So there's a difference between at most and fewer. Do we all see that? Do we all understand there's a difference between at most and fewer? At most means you're going
Yes.
to include, fewer means that you do not include. And so look, this is what happens in the binomial distribution need to be true or false. If it is false, it calculates exactly. It's calculating the PDF. If it's true, it's calculating up to and everything below or to the left. To the left of the numbers, how we say that. So that presents a problem because we can only do true or false. But we have one more thing we need to look at, which is at least or more than. And if we're looking at least or more than, well, that's going to change some things, right? Because we don't have a formula for that. We only have true and false. So we can only do 2 of them, right? So it says getting, again, I don't like this, at least, getting at least 5 questions correct. What does at least 5 questions mean? That's the probability that x is what?
5 or more.
5 or more, greater than or equal to 5. So on this table, that would be all of these probabilities, right? You understand that? This probability that x is greater than or equal to 5. There's a problem here. The functions I have either calculate at exactly, or they calculate up to and below. Up to and below. So how am I going to calculate at least 5 if I can only use those 2 functions? What do I have to do? Anybody got an idea?
Did you change your numbers?
I mean, how? Changing the numbers won't work because it's still calculating at and below.
Would
I'm
you
actually trying to
just
calculate. Keep going.
would
I'm
you
listening.
just find the lesser ones and then subtract that?
Great job. So we're going to do. We can find up to 4 easily. We can find that easily right there. We know that the green and the red have to add up to what number, by the way?
1.
The green and red, we have to add up to 1. So here's what I can do. If I want to find the probability x greater than or equal to 5, I can do these we know have to add up to, they must equal 1. So we can do 1 minus. 1 minus what will get me greater than or equal to 5? Can anybody tell me? 1 minus probability of x is what?
Greater than or equal to, or less than or equal to 4.
Good job. That's how I find greater than or equal to 5. I do 1 minus probability that x is less than or equal to 4. I take away everything to the left of 5 from the number 1. Excel can calculate to the left with no problem. It can't calculate to the right though. And I want you to realize I can see all this because I've drawn this table that I've given you right here. I would recommend you drawing a table like this to do these type of problems. If you have 12 things, go from 0 to 12. If you have 7 things, go from 0 to 7. If you have 20 things, go from 0 to 20. Because I'm able to box in what I want to look at now. And I can look at it and see that I need to calculate everything to the left of 5. And so in my calculator, here's what I'm going to do. For 4, you can do 1 minus, we do this, binom.dis. 1 minus binom.dis. Remember, number of successes is 4. 12 things, 0.2. And I want to calculate up to 4. So this is true. That's true. So greater than or equal to 5 is 1 minus probability that x is less than or equal to 4. I take away everything to the left of 5 to calculate this and subtract it away from 1 because they all have to add up to 1. And so when I go back to Excel to calculate this one, here's what I'm going to do. I know this is the probability that x is 4 or less right now. Do y'all see that? It's 4 or less already. So to find the probability that x is greater than or equal to 5, I do 1. I do 1 minus this probability right here. That is the probability that x is less than or equal to 5. 0.073. You can actually put that all into one box if you wanted to. You could do, I just got tired of writing it, but you would do 1 minus binom.dis 4 12.2 cumulative true. And that's how you get that value too. Either way, you can do it in parts. You can do it in one big step like I just did it. But it'll give you the answer 0.073. What is the probability of getting more than 5 questions correct? How is that different? Getting more than 5, what does that mean?
Probability that x is greater than 5.
Probability x is greater than 5. Greater than 5 means what in this distribution then? 6 through 12. This is the probability of x greater than 5. How would I calculate that?
Same thing, but you put 5 for the,
Put a 5 back there,
part
no
of the
good.
binomial.
Take away this orange part. So it'll be equal to 1 minus, right up first, the probability that x is less than or equal to 5, which is 1 minus binom.dis 5 12.2 true. 512.2 and true. We're going into Excel, change this 4 to a 5. 0.019, 0.019. And now a very common one that you will see a lot of, a very common one is the probability of getting at least one of something correct. At least one. Well, how do you calculate at least one? What does the word at least one mean? That's the probability that X is what?
Greater than or equal to 1.
Right. So that includes everybody except who?
1.
Who does that include? That includes everybody except who?
0.
Except 0. So to calculate this, at least one is a very common thing you will see. It's always 1 minus the probability that X is less than or equal to 0. Technically, you can do equal 0 because it doesn't matter because 0 is the only thing that's there. But in this one, you would just do 1 minus the probability, or 1 minus binom.dis 0, 12.2. You can do true or false. I would keep it with true because you're calculating at least, and at least is always going to be a true type of problem. So when I calculate that, again, I'm going to change this 5 to a 0 in the front. I get a 0.932, a 0.931. Probability you get at least one right equals 0.931. That is the binomial distribution. That is everything you need for this test. I will play